G'day viewers, in this episode we're going to talk about cosmology calculators. In fact, we're going to look at one specific cosmology calculator developed by the International Centre for Radio Astronomy Research, Icrar, based in Perth, Western Australia. Icrar is a collaborative venture between Curtin University and the University of Western Australia. If you are a cosmology connoisseur, you will recognise their calculator as being gourmet. In my opinion, it is the best cosmology calculator freely available on the internet. You can find it via the link appearing at the top of the screen. The way we will move through this video presentation will be to look at a few important screenshots, then we will look at a screen recording of key functionality. Okay, let's get into it. When you load the Icrar Cosmology Calculator and navigate to the Calculation tab, you will see two bodies of information. On the left-hand side, you'll see the inputs, and on the right-hand side, you'll see the outputs. Of all the inputs appearing on screen, the most important have been emphasised by the purple boxes. These comprise of redshift Z, Hubble constant H0, pressureless matter density parameter omega m, and dark energy density parameter omega lambda. The default dataset to load is identified as reference set 737. If you look at the underlying values appearing inside the lower purple box, you can see where the identifier 737 gets its name. That is, from the first digit with respect to H0, the last digit with respect to omega m, and the last digit with respect to omega lambda. You will also see from the underlined cosmological age values on the right hand side of the screen that the results do not align with the particle data group 2023 cosmological age estimate of 13.797 gigayears. So, given the fact that the cosmological age results of reference set 737 don't align with the particle data group 2023 estimate, what does this mean for us? Well, from an electrogravimagnetics perspective, reference set 737 isn't meaningful and we may simply discard it. This doesn't mean that it has no value to astrophysicists. It simply means that it doesn't have any value to the electrogravimagnetics construct specifically. Okay, let's look at another reference set. The next reference set in the drop-down menu is identified as 137. Once again, we can see how the identifier 137 is formulated, that is, in the same manner as reference set 737. We can also see that the cosmological age estimates on the right-hand side of the screen do not align with the particle data group 2023 estimate at the bottom of the screen. Therefore, for the same reasons specified on the previous slide, we may discard reference set 137 with respect to the electrogravimagnetics construct. Okay, let's now look at the particle data group 2023 astrophysical inputs. As you would expect, when we input particle data group 2023 astrophysical data, we obtain the published particle data group 2023 estimate for cosmological age. This confirms that the Icrar cosmology calculator is functioning correctly with respect to the standard model of cosmology. Let's now take a look at what results we get when we plug in some of our own data. Firstly, I will point out that the particle data group 2023 sigma 8 value has been left in place. It doesn't actually impact the results we're interested in, so I've left it as is. Please also note that I've left the redshift value Z as 0. In the top right hand corner of the slide, you will see the link to the research article containing the data utilised. When we populate the fields indicated within the purple box, we obtain a cosmological age of 13.761 gigayears. This does not align with the particle data group 2023 estimate of 13.797 gigayears. Somehow, we seem to be missing 36 million years. If we consider the particle data group 2023 estimation error of 23 million years, then overall we are only actually missing 13 million years, which needs to be explained. We will address this discrepancy going forward, but for now we will set it aside. On the next slide, we'll look at the contribution and effect of dark energy redshift. As you will be able to see, including the dark energy redshift as indicated by the upper purple box, some important changes occur. Please note that the dark energy redshift takes a negative Z value. The reason for this is explained in the research article referenced via the link in the top right hand corner of the slide. Please take the time to review the research article. The effect of the negative Z value is to conclude that the true age of the universe is equal to the Hubble age. In other words, according to this cosmology calculator, the universe is approximately 842 million years older than the standard model of cosmology predicts. Please refer to the look back time at Z, which has been underlined near the top of the calculator. This so-called extra time fixes the absurdly rapid evolution of galactic structures problem experimentally observed via the James Webb Space Telescope. At the time of the creation of this video presentation, large galaxies have been observed to exist far sooner after the Big Bang than the standard model of cosmology predicted. However, many cosmologists have seemingly accepted this miraculous observation without reaching for the most obvious explanation for its absurdity. That is, the standard model of cosmology calculation for cosmological age is flawed. In other words, the universe is not 13.8 gigayears old, it is 14.6 gigayears old. It is equal to the Hubble age. Please refer to the stated research article for a detailed explanation. Let's now come back to the 13 million year discrepancy we identified earlier. The question we need to answer is, why does the Icrar cosmology calculator generate a minor discrepancy when utilising our inputs? Or in other words, why doesn't it generate the particle data group 2023 estimate of 13.797 gigayears precisely? Well, to answer this question, let's take a look at the calculation contained in our research article. Appearing on screen is an extract from our research article. At the top of the slide, you will see the link to the research article, and at the bottom of the slide, you will see the link to the actual calculations, executed in a MathCAD computational environment. You can see from the underlined results appearing on screen that the particle data group 2023 estimate for cosmological age is reproduced precisely within the electrogravity magnetics construct. This implies that the Icrar cosmological calculator contains some unidentified logic hard-coded into the application which is not obvious to us and cannot be accessed for inspection. It could also be due to the fact that the application was developed in 2015, as claimed by the developers at the bottom of the slide. Hence, outdated physical constants lurking in the background may be the culprit. Unfortunately, there is no way for us to know without investing more effort at the source code level. Therefore, based upon our computed results appearing on screen and the supporting dark energy refractive index calculations referenced on screen, we may confidently conclude that the 13 million year discrepancy under consideration is not due to the electrogravity magnetics construct. Rather, on balance of probabilities, it is due to some other influence. So, let's see if we can figure it out. To facilitate further investigation, let's review some of the other inputs on the Icrar cosmology calculator. There are three inputs we haven't paid too much attention to so far. We will look at them momentarily. However, for now, please briefly pause the video presentation and take the time to read the information appearing on screen before moving on. The first input we'll consider is the effective mass density of relativistic particles, omega r, that is, photons and neutrinos. Since we are interested in aligning the Icrar cosmology calculator with particle data group 2023 results and the electrogravity magnetics construct in the present epoch, we can disregard omega r by leaving it set to the default value of 0. We can do this because the present epoch is matter dominated, and omega r is more influential and relevant to a much younger universe scenario. That is, when the characteristics of the universe was dominated by radiation rather than matter. The second input we will revisit and consider more carefully is the sigma 8 parameter. We can pretty much disregard this input too, because it deals with matter density fluctuations, particularly in relation to galaxy cluster observation data. However, for the purposes of our investigation, we are more interested in the big picture. Hence, we can utilise the Icrar cosmology calculator default value, or we can standardise on the particle data group 2023 value for the sake of consistency. The last input we will look at is the dark energy equation of state parameter W0. So then, let's plug the particle data group 2023 estimate into the calculator and see what results we get. When we input the particle data group 2023 value for dark energy equation of state parameter W0, we see an immediate improvement. we obtain a result for the redshift independent cosmological age of 13.815 gigayears. This means that our revised result falls within the particle data group 2023 estimation error tolerance of plus or minus 23 million years. The difference between our revised result and the particle data group 2023 value of 13.797 gigayears is merely 18 million years. Hence, we have successfully aligned the Icrar cosmology calculator to the particle data group 2023 estimate and the electrogravimagnetics construct. Okay, let's now see if we can strike a perfect match. By trial and error, we obtain a perfect match for the redshift independent cosmological age of 13.797 gigayears when W0 equals negative 1.0185. This result fits within the particle data group 2023 estimation error tolerance of plus or minus 0.031. Let's now see what happens when we align the redshift-dependent cosmological age with the Hubble age, as per the electrogravimagnetics construct claimed that the true age of the universe is equal to the Hubble age. Once again, by trial and error, we can align the redshift-dependent cosmological age with the Hubble age when W0 equals negative 0.9825. This value sits slightly outside the particle data group 2023 estimation error tolerance, but not by much. The lower particle data group 2023 limit is negative 0.997. However, our result sits slightly beneath this limit, as appears on screen. Importantly, our result is close enough to the particle data group 2023 lower limit that we can give it serious consideration. Okay, let's now summarise what we have learned. On our journey, we have learned three important lessons. Number one, the Icrar cosmology calculator is accurate. Number two, the universe is approximately 842 million years older than the standard model of cosmology predicts. Number three, the dark energy equation of state parameter W0 sits between the limits shown on screen. Okay, let's move on to the screen recording session we mentioned in the introduction. Here is the Icrar cosmology calculator as it appears when you load it for the first time. On the left hand side you'll see the inputs, and on the right hand side you'll see the outputs. Let's just run through some of these fields. The redshift value over here, the default setting is 1. I don't know why they choose that, but they do. What I tend to do is bump up immediately the significant figures to 15. You'll see here the reference set that I talked about previously. So it's a drop down menu, and you can see reference set 737, 137, Planck 18, etc. I'll just click on some of those. So let's just have a look at 737 for a moment. Now you can see that the, and I explained previously how this came about with a 7, 3, and there's actually a 7 there, which I sort of talked about before, but let's just step over that. So you can select the reference set, then you click calculate, and you get your result on the right hand side. So we'll do 137, click that result. You'll see the numbers over here have changed. Same deal with each one of these other drop down reference sets. You can just get through them. They've got Planck 18, Planck 15, Planck 13. Let's just try Planck 13, play with that. See numbers change, and they've got WMAP reference sets, etc. They've got a Millennium one. I believe that's set at around the time when, I think around the year 2000 or something like this. Anyway, so you've got a variety of configurations here. Now, I'll also point out other stuff that I've got on open on my screen that we'll actually use a bit later on. So I've got the particle data group here, 2023 values. You can see the Hubble information about the Hubble constant there. You can see sigma 8 stuff here. You can see down the bottom here dark energy equation of state. So we're going to use some of those numbers just momentarily, but I just keep them sort of handy. I've also got open the dark energy refractive index calculations that I mentioned in the presentation. And here's the actual MathCAD file generated, so you can see that it's all there. I'll put that on screen because I did talk about it earlier, so I just wanted to show you that does in fact exist. You can look that up if you want to.
I've got also open a key article, the existence and effect of dark energy redshift on cosmological age. I've also opened up table 1 from that research article. This information is where we're going to get most of our plugin values, so I tend to have that open so I can copy and paste. So let's just go through and populate it with information that's relevant to the electrogravity magnetics construct. So I'm going to go over here and I'm going to plug in my redshift value. I'm going to do that over here. Make sure it's got a negative in front of it, like so. You can also, what I'll do here is, just because it's a bit easier, you can plug that formula in there just as I have done, and that'll just give you one less thing to actually do. Now I'll copy and paste this other information here. That was the Hubble constant, I think, and I'll copy and paste my mass parameter here, pop it in there like so, and then I'll just put the particle data group value there, and if I can look up this, whoops, if I can find it, where'd I put it? Oh yeah, here we go. So that's the one of the particle data group values. I just paste it there. Now I'll grab this one here. Okay, and I'll put that one there. Make sure we've got a negative out the front of it. Okay, so I've pretty much now populated what I need to. So I'm going to, for this purpose, so I'm going to click. Okay, so once you click calculate, you can see over here that we reproduce the age value that we talked about. It's closer to 13.797 gigayears particle data group value. So now if we put in, I think it's this. Let's have a look here. If we put in that value, yep, see we get the universe now is 13.7996. We're a bit closer than we were before. I forgot that value there. Okay, there we go. So now we get exactly 13.797. So everything lines up. So you can see pretty clearly that once you put your information in, just click calculate, and it's all good. Pretty easy calculator to use. You can see up here the look back time, about 842 million years. So this is what this calculator now with my inputs is claiming. It's claiming that the universe is in fact 842 million years older, and this tends to solve or fixes the some of the observation problems that have been encountered with the James Webb Space Telescope observing large-scale galactic structures forming very soon after the Big Bang. So that's it, viewers. It's a basic run through of key functionality of the cosmology calculator.